Professor.
Oh, hi, Tram.
What are you working on?
Well, I'm working on a demonstration of the Affinity Laws.
Infinity Laws. Like to infinity and beyond.
Oh, no, nothing like that.
Aw.
It's the Affinity Laws. It's called Affinity because, well, here, let me explain. Suppose we have a tank of water and we want to pump this out to a system, for example, like the city water supply. So I have a pump right here and we want to be able to control the flow of that water out to the system. Now we call flow Q.
And why do they call that Q instead of F?
Well, that's because, I don't know. Maybe you could Google that for us.
Okay. Well, how do we control the Q?
We can control that with a valve on the output right here.
Like a kitchen faucet.
Exactly. And with that valve, as you crank it on down, it reduces the flow, and then it reduces the pressure, and then what it also does is it reduces the power that's needed for that.
That's interesting.
Yep. Now, what we could also do, though, is we could put a bypass valve on this thing.
And how does that work?
Well, what it does is it takes some of the discharge water and it sucks it back into the input side.
That means less water for the system.
Yes, it does. But the problem is that the pump sees the same amount of water all the time.
Well, that's not very efficient, is it?
No, it isn't.
What else can we do?
Well, what we can also do is we can slow down this pump. And by slowing down this pump, that's where the affinity laws come in. Because the flow is proportional to the speed of that pump. And the head pressure is proportional to speed squared. And the power, which is the important part, is proportional to speed cubed.
Does that mean we could save energy?
It sure does. For example, suppose we're running at about an average of 70% of flow. With 70% of flow, we would save about 60% of the energy that way.
Yeah, but does that really work? Looks like a bunch of fancy curves and equations to me.
Well, that's a good question, Tram, and let's find out. Let's go over here to this contraption.
What is all this stuff?
Well, let me explain. What we have here is a tank of water and a pump and a motor running that pump. We've got a valve on the output, and we've got some instrumentation so we can measure stuff. So let's see if we can get this running. Tram, could you push the start button right there?
This one.
Yep. Great. Now let's open the valve all the way. So what do we have for our flow?
About 39 gallons per minute.
Okay, and what's the power?
Power is at 364 watts.
Okay, we'll mark that here on the board. Now let's close the valve down so we get about 70% flow. So 70% of 639
That would
is
be about 25 gallons per minute, right?
Yeah, that's right. So with 25, now what's the power?
We're at 298 watts.
298. Okay, so that's this point right here.
So we're
going
saving
along.
about 66 watts. The power didn't go down much, did it?
No, it didn't. But instead, let's slow down that motor.
How do you do that? I thought a motor only goes one speed.
Well, usually they do, but if you have a variable frequency drive, you can actually change the speed of the motor.
Like this one.
Exactly.
How does that work?
Variable frequency drives, sometimes they're called VFDs, sometimes they're called ASDs, sometimes they're called freak drives. But what they do is they change the frequency of the voltage going to that motor. And by slowing down that frequency, we actually slow down the rate of the rotation of the magnetic field inside of that motor, which means the motor slows down, which means the pump goes slower, and with that you get less wear and tear on the pump, and with this you got savings which are just incredible.
Are you okay, Professor?
Yeah, I'm fine. Let's get this set up again. Let's open the valve all the way. All right. And what do we have now for the flow and the power?
We're at about 39 gallons per minute.
Okay.
And 364 watts.
Great. Back where we started. All right. Now we're going to have to slow the motor down to about, say, 1200 RPM.
Professor, we are at 1200 RPM.
Perfect. Now what do we have for flow and power?
Flow is about 25.7 gallons per minute.
Okay.
But now the power reading is only 144 watts. A savings of 220 watts. That's almost 3 times the savings. Wow, this really makes a difference. But are we also saving money?
We sure are. In fact, electricity usually costs about, say, 10 cents a kilowatt hour. And for a little demonstration like this, we would be saving, let's see, how much would that be?
About $200 a year.
Yeah, about $200 a year. But a real system would be about 500 times bigger than this. That means we'd have 500 times the savings, which would be about...
$100,000. That's a lot of books.
Yeah, it sure is.
But is that all there is to these affinity laws?
Yeah, that's pretty much it. It's really quite simple. Again, flow is proportional to speed, the head is proportional to speed squared, but the power which we pay for is proportional to speed cubed. But you know what? You don't get quite as much savings if you have a system like this where you have a fairly high static head.
Static head? Like what's happening with your hair, Professor?
Wow, what's wrong with my hair?
Okay, I gotta go. But thanks for answering my questions.
Yeah, you're welcome. Let's see, where was I? Oh, yeah.